Hi, Doug from Bug Amps. So for today, I'm going to do something I've been wanting to do for a while, which is I've been kind of wanting to sort of showcase and also just put out there for any other DIYers, some of the designs that I've made throughout the past couple of years. Sort of funny little amplifier designs that maybe other people want to build. And just to sort of explain like what went into the design and how they work and just that kind of stuff. And to sort of, we could also, I think we'll test these since it's been a while since I built them, a couple of years maybe, or a year or more in some cases. There's a lot of things I'd probably do differently now, and it'd be interesting to sort of give them a test, see how I did, sort of give myself a grade. And so first one we're going to go look at here is this little guy right here. You can see it. It's a GU-17. So it's a really cool little tube. It's actually 2 pentodes in a single bottle. It's a little one on the outside. And the driver tube here is a 6H8C, which is just a Russian 6SN7. And you can see I've got these vintage output transformers. They're from a GE receiver that I got on eBay. And kind of look at the top here. You can see I've got some test points for setting the bias on the top and the speaker outs and everything like that. And on the back, all we got is just the power receptacle and on-off switch, and the bottom sort of vented case right there. And we'll pop the bottom on this at some point. But first of all, you can see behind me here I've got the circuit. So let's look at this, and I also have the power supply circuit we'll look at here in a minute too. So I hope you'll find this interesting, and let's get to it. All right. So to get started with, I wanted to show you a few little things I made to design the amplifier. So the way I design is I'm not doing this in Spice. I have an idea. Usually it starts with a tube. I find a cheap tube on eBay or something that's really cool. In this case, the tube in question was the GU-17. So you can see here, got a GU-17. I found a bunch of these tubes cheap on eBay, and I thought, man, what can I do with these things? And so you can kind of see here, you've got 2 plates. You've got a single suppressor. It's not a suppressor grid, a single beamforming plate there. You can kind of see it. You're also going to have a single screen, so you got a single G2. But then you've got two separate G1s, which I guess you could say it like that, and then a single cathode, right? And so what that means is that you can do a push-pull amplifier, a pentode push-pull amplifier output stage with a single tube. And so I can get 8 watts, nice clean 8 watts out of a single tube. And these things are cheap and cool. Anyway, that's where it started. And as you can see, I've made a little test jig here. Maybe I don't know if it's focusing my face, but I'll just put this right here so you can kind of see how I did this. Now you can see there's resistors on there. I just put minimum stopper values right on the pins because you don't want to keep the stoppers too far away, you know. And then I've just got screw terminals for everything else, right? So it works awesome for breadboarding. Okay, so the next thing I've got is the transformer. So you can see on this, I've got a transformer input. And I found these really good cheap 615K transformers on AliExpress, and they aren't all good. You have to get them from the right place, but these are really good. And so you can see I have soldered it onto an octal base, and now I can prototype breadboard with these little transformers. They're really cool. So you can see I've just got screw terminals again. Yep. And then I've got my input, my driver tube here. It's not really the input stage. The input stage is really a transformer on this one. You get gain from the transformer, voltage gain. But this is the phase splitter driver right here. And it's a Russian 6SN7, which is 6H8C, but it's pin compatible. So you can see I've got the minimum stoppers just soldered right on there. Yeah. And screw terminals once again. Yeah. So what I did was, once I had designed the amplifier, I went up and made PCBs for it. And you can see that the little transformers just fit right on the PCBs and solder in. So pretty cool. Whole amp sort of sits on there, and then the power supply board, just like this. On here we've got high voltage, we've got screen supply, and we've got low voltage to send to a DC power supply for the 6H8Cs, which I didn't actually show in my power supply schematic, but I'll explain it. Anyway, so now that you've seen all that kind of stuff, and yeah, I think that's everything I had. Now that you've seen that kind of stuff, the way I designed it, I'm going to switch lenses here, and we'll zoom in on the actual circuit and explain what's going on. Let's get into the actual circuit here. So when I design amplifiers, I always design the output stage first, because you don't really know what you're going to need, and as far as driving signal until you have the output stage going. And so also because sort of the unique aspect of this amp was this really cool GU-17 tube, and I also already had these cool vintage GE output transformers. I just started there. And so all I did is I got my variable voltage bench power supply out, and I got a negative supply going, right? So you build your supplies first. And then I just got my output tube set up, and I got my power tube set up, and I just applied an arbitrary negative voltage to the grids and started cranking up my high voltage until I sort of reached a point where the tube was operating at a normal operating point. And so that ended up being at about 16 milliamps per side with about 315 volts on the plate. And I'm sorry, I also got another supply out for my screen supply, so I ended up with 220 volts on the screen. And this was all found just empirically. So interesting thing about the GU-17 is that a sort of interesting problem that you have to sort of face up to when you're doing a push-pull stage with the GU-17 is that you don't know that your tubes are balanced in current, because the current for both of the sides of the GU-17 are coming from the same cathode. And so you can't just put a little resistor on the cathode to discover what your current is, right? And so I had to put my current sense resistors actually in the plate circuit. And you might think, well, maybe that's not a great place for a current sense resistor, and you'd be right for a couple of reasons, but you might be wrong for another reason. So the reason that you might be wrong is that for a pentode, the plate impedance of a pentode is very high, something like 20K or higher, right? And the primary impedance of this transformer is going to be, it's 8K across, so it's 4K per side, right? And so the inclusion of 10 ohm resistors in that circuit is very meaningless. It's certainly less than DCR of the primary of the transformer, and so they affect the circuit almost not at all to be there. The reason it's not that great to have those there is that when you're setting the bias on this amp, you're probing high voltage. So you're actually probing, the test points probe, the plate voltage of 315 volts, and so keep that in mind. It's probably why an amplifier like this maybe isn't meant for mass production, but more of a hobbyist sort of amplifier, because you don't want average Joe or whatever probing high voltage to set bias current in the tube. Another thing you'll notice here that's kind of interesting is I've included, and well, actually when we're testing the amp, I'm going to show how this works, because I'm actually kind of proud of how this works. But you'll notice here we've got a 220 volt screen supply, and it's going through this 1K resistor to the screen. But in parallel with the 1K resistor, we also have a 10 ohm resistor, a 12 volt Zener, and a red LED. And so what's all that about? That is actually a clip detection circuit. So in a pentode output stage, you can tell that the amplifier is at or near clipping when the screen begins to draw significant current. And so when the amplifier is operating normally, there's so little current that it doesn't develop enough voltage across the 1K resistor here to turn on the 12 volt Zener, right? And so, but when the amplifier is close to or at clipping, there is enough current to drop enough voltage across the 1K resistor to turn on the Zener and then turn on the diode. Now what's the 10 about right there? That's just current limiting for the diode, so that when the diode's on, it's just not a dead short there, you know. So it keeps the red LED from potentially burning out or something like that. And so that's what that's all about. It works great because it's load dependent. So if you have a smaller load or a higher load or whatever, it doesn't matter what your load is, the amplifier will begin to clip around the same time that the screen begins to pull significant current. So it's an excellent clip indicator. And it's really fun because this is only 8 watt amp, right? And you would think, well, 8 watts is hardly anything. But I was surprised. Having that clip indicator was really fun because I could crank the heck out of this amplifier and the clip LEDs would hardly ever come on. And so I was like, 8 watts can really do a lot more with a pair of moderately efficient speakers than you might think. And so having that clip indicator was really fun. It was sort of eye-opening, like how much sort of bang you could get for 8 watt, little 8 watt amp. Really cranks. All right, so yeah, so we've got a way to check our bias. You'll see we've got negative voltage input here for our bias, and our sort of bias resistor there, the load. What the resistor is going to be loading the signal from the previous stage is 200K on both sides, which is sort of a typical value for the grid of this tube. You can see we've got 1K stopper resistors, and those are actually soldered onto the little board that I used to test this. And obviously, if you're creating a PCB or something like that, you just put them right on the grids. Or if you're doing this point-to-point, you could totally do this point-to-point or turret board, or however you would like to construct this. 1K is pretty typical, right? So I just sort of guessed, you know, with stopper values, you just sort of put them in. If you get oscillation, they're not high enough, and so 1K, haven't had a problem with that on power tubes. It's a pretty typical value. You can see that the suppressor grid, or the beamforming plate in this case, is just tied. I think it's tied internally to the cathode. Like I said, we have a single cathode. We've got a single G2, but we've got separate G1s, and we've got separate plates. And that's pretty awesome. So anyway, so you don't even have to have any of this other stuff. You can set up, you just AC ground the grid inputs to your power tube, and you can just turn it on and bias it up and make sure the operating points are right before you do anything over here. And so once you've got your operating point where you want it, you'll know what the negative voltage is on the grid for your operating point. And that is the key component that you need to know how much voltage you need to swing into this, because you can see it's about negative 22 volts here. So if it's a negative 22 volts, that means it can swing up to 0 and symmetrically down to 44. And so we need a driver stage that can swing 44 volts clean into this to clip it. You know, it's pretty basic stuff, right? But you would never have known that if we were designing the driver stage first. We might have spent all our time designing a driver stage and then realized we had not enough voltage swing or way too much voltage swing or whatever, right? And so that's why you design the output stage first. All right, so now let's talk about the driver stage. So the driver stage is interesting here. Like I said, it's the equivalent of a 6SN7. So it's got what, like a gain of 30 or something like that. And so that wouldn't probably normally be enough to drive this tube, but you can see I've included this the 600 to 15K input transformer, right? And so that gives us gain, the gain that we need to drive this and to run our negative feedback, which we'll talk about in a minute. And so you can see the operating points here are a little bit wonky. These were found empirically, so I rolled through different operating points to find the right ones. I actually see this value right here. In the actual amp, I left that as a variable resistor, a little 20-turn precision pot. And the reason why is because the combination of an LM317 and a variable resistor there, so you put the variable resistor between the V out of the 317 and ground, and then you tie the adjust to ground, right? And so what a 317 does is it always tries to give you 1.25 odd volts across the adjust pin to the output pin, right? And so if you know the voltage and you know the resistance, then you know the current. So it becomes a current source. So it's a little current source, and if you have an adjustable resistance there, that means that you can roll through various currents. Now, both of these tubes are sharing the current from this current source from ground, you can see. And so if we know the current flowing through the tube, and we know the value of the load, which in this case is 18K, then we know the drop across the load. And so if we adjust this here, we adjust the drop across the load, which means we adjust the plate voltage. We adjust the cathode voltage, which sort of adjusts the headroom in between the grid and the cathode to a certain extent. So we can adjust all of those things with a variable resistor there. And so basically what I did is I took like an FFT, you know, you get like your FFT and your scope, but I actually used one on a computer, it's a lot more accurate. And I just put in like a 1K signal, and then I just rolled through the various values for this resistor until I found the lowest distortion operating point for that tube. And it ended up being kind of interesting. It ended up being a little bit wonky. Like, this is not an operating point that you would pick using a load line for this tube. It's a little bit cold. You can see the plate voltage is a little bit high. So let's see, we need to swing 22 up and down, so we still have plenty of room to swing 22 up and down. But this stage could swing a lot more if the plate voltage was halfway, for instance, halfway between the supply voltage and the and ground, basically, or the cathode voltage. But in this case, this still made full power, and it actually had a lower distortion characteristic. But like I said, I left a variable in there. So if I wanted to change the operating point of this driver stage down for a more sort of a higher headroom into this tube, I could just pop the top on the amp and do that. So that's what I'd recommend for you. Give it a try. It's a lot of fun being able to just really easily adjust the operating point of the input, the driver stage. Now, this is drawn a little bit funny. This is the way I like to draw a long tail pair, but this is a differential stage, a long tail pair. You can see that the cathodes are connected together and they're sitting on a current source. So all of the DC flow is flowing from the supplies through, this is conventional, obviously electron flow, it's coming from the current source and then going out through the tubes like this. But that's where all the DC now. Current sources are very, very high impedance in the realm of AC signal. And so with a current source, all of the AC of a differential stage travels through, it travels up and down. I could draw like so the DC goes this way, right? The AC is all like this, right? Like that. And so the cool thing about that is that you end up with equal and opposite phase split because you know that all of your AC current is going to be flowing through both of your resistors. And so your accuracy is only limited by how high the impedance is of your current source, which in this case is adequately high, and how closely matched your load resistors are, which in this case is as close as you want to match them. Just get your multimeter out and find some good ones. So that's what's happening here. You can see I've grounded the grid here because the differential stage only amplifies the difference between the grids, the inputs here. And so if I ground this grid, then it's always amplifying whatever's on this side because that side is always different than nothing, right? And so if it swings up or down right there, the whole thing amplifies. And of course, like I said, the output is phase splitter, so it's equal and opposite. Hope that makes sense. You can see I've got a grid stopper here on the input grid. A 300 is just another one of those ballpark figures, and if it oscillates, you go higher, but low as you want without oscillation, you're fine. You can see that my supply voltage is a little bit lower than over here because I've just added another stage of like another RC. We'll look at the power supply in a minute. And then the input here, like I said, we've got this transformer. And so I really like these little transformers from AliExpress. And I guess I'll link in the video description, that specific transformer. Now let's talk about the negative feedback, because the negative feedback I've done weird, and I think most people would say I've done it wrong. And I don't know, maybe I have done it wrong. I knew that I was doing it this way on purpose when I made it, and I had people ask me the question. I'll give you the general reason that I did it this way. The first way I did it was I swapped primary sides, right, to change the phase, and then I brought this back around to the grid on the other side of the long tail pair. And that works great. That's the way most of these do, you know, they come back around to the other side of the long tail pair. It's a good place to inject some feedback. You can also inject it into the cathode, but I wanted to try injecting it back into the grid of the first stage, so I swapped those back again and put it in here because I wanted to just see, just to find it interesting, how well the secondary would load it. How well would the secondary of this little input transformer load the feedback? And as it turns out, it loads it great, loads it really well. The problem with this is that the loading of the feedback, and thus the output impedance of the amplifier, is somewhat determined by the source impedance driving the amplifier. And so you might think, oh, that's a big problem because you're going to get less gain and more feedback the higher your source impedance is. But in practice, it's not that big of a deal because these little transformers, they all require something between like 400 and 600 ohms to drive, or else they don't achieve full bandwidth. And so this is not the kind of amp that you would want to run passive volume in front of. It doesn't have a high input impedance, it has a low input impedance, and so. But that's not really a problem because any modern DAC or any modern sort of preamp with a buffered output or anything like that, like I've been running this with a DAC, but I also used to run it with a little mini DSP, which has a buffered output. Anything basically with a buffered output is going to have the correct impedance to drive this, and so you really, even though it's a variable, it's not going to vary a lot. It might vary between like 400 and 600 odd ohms or something like that. And so the level of feedback doesn't change that much, right? So you can see that we have feedback here, and we have a ratio between whatever this value is, which is generally like an 18K range, I think. We got a 24K here, and you can see we've got a little compensation cap there, which you tune by injecting a square wave in. And you just tune that little cap there, so your square wave looks nice and clean. And we'll see if I did that right. Well, when we test the amplifier, we'll double check that I didn't screw that up. So that'll be interesting. And right, so how did I choose this amount of feedback? Well, I wish I could say that I designed it from the beginning to have this much gain so I could have this much feedback. That's simply not the case. I increased the feedback until the amplifier was clipping at a reasonable input voltage of around 1.5 volts RMS, looks like here, which is actually, it's not a very sensitive amp. Like, it needs a decent driver, right? The usual modern DAC can achieve 2 volts RMS, so a modern DAC will be able to clip this circuit just fine. And you can see that with this amount of feedback, we've ended up with an output impedance of 6.5 ohms, which is kind of high. It's like, it's not a super low output impedance amp. Like a lot of loop negative feedback amps sound kind of solid statey because their output impedance is rather low. Here's loop feedback pentode output amplifier, only makes 8 watts and has a very tubey 6.5 ohm output impedance. And so if you like that kind of thing, which I actually kind of do, I like a moderate, not a high output impedance, but I feel like things get kind of sterile in the music listening department. Down in the 3 or 4 ohm range is sort of my limit. If you get lower than that, and obviously it depends a lot on speakers. Right. So we got coupling caps here. Those were picked empirically. The way you pick coupling cap, the way I pick coupling caps is I run a frequency sweep, and then I put a bigger cap in there, and I run another frequency sweep, and if my low range improves, if the low range comes up, I put a bigger cap in there. And then I run a frequency sweep, and if my low range improves, I put a bigger one in there. And I do that until the low range does not improve anymore. And once the low range has reached sort of its maximum or whatever that it's going to reach with the rest of these components, I call that my coupling cap value. And in this case, it was pretty small, 0.05 UF is all we needed for full frequency response of this amplifier. And it's got a good full frequency range. Like, it's actually a really good performing little amp, and we'll check on that when we actually test the unit. All right, so that is that. And next thing we're going to do is look at the power supply. All right, let's talk about this power supply. So in this case, I went with a Antec. So it's a 100 watt Antec. And so if I remember right, it's going to be like AS 100-300 something. I don't know. I'll have to look up the actual number or something like that. But anyway, it's a 300 volt secondary, 120 volt primary, Antec. It's got a couple of 6.3 volt windings, right? I've just paralleled them up here in this. But in the actual amp, I ran some of these. I think I paralleled them up and then I ran it into a DC converter. Yeah, I DC rectified it and then I switch mode rectified it and then I regulated it. So we'll talk about that later. It's not necessary for the amp. But you can see I've run the GU-17s at least, and in this particular schematic I've run all the tubes off of the 6.3 there. And I've got a bridge rectifier. I've got a thermistor on the primary that's like it sort of starts off up soft, so that when you're filling the main filter caps it doesn't sort of rush in too fast, which is kind of nice. So they're cheap and I like to put them in my amps. What else can I say about this? We've got a 1 meg to ground there. What's that for? That is for DC ground path, like discharging path. Now I don't need to have that there because up here I have a 200K and a 1.5 meg already to ground, so it would eventually discharge on its own. But I usually put another sort of like little bit of a leak there so that the high voltage doesn't stay high voltage for too long. So if somebody is opening up the amp, that's not going to still sit there be charged, right? I've got a film, little 2UF sort of film cap there. That's to dump any of the high frequency that might be coming from these diodes, right? So it's not totally necessary depending on the diodes you use or whatever. Then I've got the main filter cap here. It's 100 UF, 450 volt cap, and that's typical, sort of a typical main filter cap value. Next, we have this guy right here. What is this? This is called a capacitance multiplier. It uses a MOSFET, in this case an N-channel MOSFET, high voltage. And how does it work? Well, it's pretty simple. You've got the input here, which is the drain. You got the output, that's the source. And you've got the control grid, or in this case, the gate, I guess. And it's just like a tube, just like a pentode, in that it's basically like a cathode follower. So if you imagine sort of the plate and the cathode and the grid here, it's just like that. And so just like a cathode follower, the source follows the gate, right? And so to a large extent, the source ignores the drain as far as ripple goes, and just follows the gate due to the large gain of the device, and the gain is between the gate and the source. And so if the source tries to stray away from the gate, it uses the full transconductance of the device to sort of keep itself in line. All right, so all we got to do then is just make the gate super nice and clean, and it's easy to do that because the gate doesn't really consume any power. You don't need any power. It's not like a transistor. It don't have to supply any current to it. So that means that you can make an RC filter that is very, very high value with not very big components, although I did use a couple of big components here, and I'll tell you why in a second. So we have 200K and a 100 UF right there. And you don't need that big of a cap. I use that cap because if you use a big cap like that, you get a time constant that's so large that you get a nice soft start for the whole amp. And so the amp will start up really nice and soft, right? So like over the course of 30 or even 60 seconds, depending on the values you choose, high voltage will hit you immediately, and then high voltage will just slowly climb up there, over there, and allow the filaments time to sort of warm up and for everything to kind of get going. Right. So this value right here is a stopper. 1K, something like that. It's good. Put it right on the pin of the FET. If you don't, you can get oscillation in your FET. This resistor to the ground, this allows you to adjust the voltage drop across the device. The voltage across the device needs to be sufficient so that when you ask for full current over here from the power tubes, it doesn't drop out, right? So the way you'd test that is you put a multimeter across to the device, take the amp from idle to clipping, and then watch that voltage and see if it drops to the dropout voltage of the device. It's usually a couple volts. And so if that voltage drops to a couple volts, you make this smaller, which increases the voltage drop across the device until you've reached a point where the device does not drop out when the amplifier is loaded down, right? Pretty easy. So then we got into the resistor. Oh, first let's talk about the Zener. MOSFETs have a voltage between the source and the gate max. It's pretty low. It's the lowest voltage of all of the sort of like voltage maxes that you need to be concerned with. And so you put a Zener there so that if these ever get out of whack, they'll never get more than 20 volts out of whack, right? And so that Zener is pointing towards the gate, right? So next we've got a little resistor there, a little bit, one more RC, and also just sort of a current limiting sort of thing right there. I wouldn't do this. There's a lot of things about this that I would change now, but I'm just sort of walking through the amp as it exists, or back when I designed it. And then that's where you tap off for the plates of the GU-17, the output stage. That's where all the current is going, basically. And then you can see down here we've got another cap right here. This is another 100 UF. This is the main filter shorting cap for the power output tubes. And then we've got a 2K right here. And then we've got another, like a 22 UF, and that is the dropping resistor for the driver supply. And so that's where we're getting that slightly lower voltage for the driver tubes, the 6 HACs, right? And it's even more filtered. So it's filtered, and then it's filtered again, and then it's even more filtered there. So it ends up being very quiet. Next, we have another FET, same kind of FET right here. But you'll notice that here, instead of just letting the gate sort of float up with an RC, we're locking it off with Zeners. So we're shooting for a specific screen voltage, and we know that the source will follow. We know the source will follow the gate there, and so we need to lock the gate off at a certain voltage. And so what we're doing is we're basically making a shunt regulator here with some Zeners and a resistor, and we're shunting some of that Zener noise down here with this 2 UF film cap, right? And then we're just letting that reference voltage go to the gate there, and then of course the source is following the gate. And so depending on your values of Zeners here, you end up with the correct screen voltage. Now, this is another thing that I would do differently. I would do this differently in future builds. This is sort of a crude way of achieving a regulated screen supply. I mean, it works fine, don't get me wrong. It's a good little screen supply, but not very elegant. And then we got one final sort of little filter cap there that may or may not really be that necessary. And we end up with a screen voltage of 200 to 220 volts. We can measure that when we actually get the amp on the bench and see where we ended up with that. And so not shown on this is the negative supply. Negative supply is simple. I added another little transformer in here. I can't remember the value I used. It was probably like a little 30 volt. 30 volts would probably get us there, because we need negative 22 volts, right? And so we'll look at this again, but here's another little transformer. Doesn't need any power. It can be like a little 1 watt, whatever. And then we put a diode in here, reversed bias right there, so it's negative right here, like that. And then we can put like a resistor here. We can put a cap to ground here, like this. Something, I don't know, what do you, 22 UF or something like that. We can put a resistor here, another little cap to ground, like that. And then what we do is we'll run a pot like this, and then we'll run maybe another resistor right here so the pot doesn't have to drop all the voltage. And then off of this pot right here, this is where we get our negative 22, right? And so this is x4, right? We just multiply this times 4, right? And so you have 4 of these little guys. They all have negative. Obviously this is grounded right here, and these guys right here get the 120N, like that. And all these values, you just adjust them. You just adjust these so that you end up with that negative 22 is sort of in the middle of your operating range, right? And so these can be large. This could be like a, you know, like a 50K pot or something like that, 20 turn little thing right there. And this could be like a, who knows, another you know, 30K or something like that. And this right here could be like a, I don't know, like a 4K or something like that. And these could both be like 22s, something like that. I can't remember what I did in the actual amp, but this is sort of a typical way of achieving sort of your negative, adjustable negative supplies for all of the grids of your power tubes, right? So that is also in the amp. I just didn't include it because honestly, I just assumed that anybody building this amp would just know how to accomplish that. Right. I also have a DC filament supply that's in this amplifier. I may go into that in another video, but it's not necessary for this. I just put it in there because I have a DC filament supply board. Let me show it to you. I've got this little board, right? And so I like to put it in amps because I build it, you know. And you know, I just run the 6H8Cs off DC because it just makes it a little bit quieter, right? So, all right. So that's that. That's one video. This video is long already. And then the next video will be actually sitting down and testing the amplifier. We'll see how I did. Give me a grade. Hopefully I did good. All right.